Advanced Calc, this is the last ice sheet. We're going to do 3 at the beginning, 4, 7, and 8. We're going to skip 10. So 3, the back half of 3 is your first assignment. So I'm just going to do a couple of these. We're trying to find the radius and interval of convergence for a series. You guys start at I. I go A through H. So I'm going to do, I think, let's do D and H. Okay. So some of these might use the root test. The book suggests you can use the root test or the ratio test, and some of the ones like M for you guys, you might use M and N, you might use the root test on, but the ones I'm going to do right here are the ratio test. If everything has a power of N, so like the last 3 for you guys, I would use the root test, but the ones I'm going to do, I'm going to use the ratio test. So D, it's n cubed over n factorial, x to the n. And I'm summing that. So I'm going to start with the ratio tests. And so this is going to be n plus 1 cubed, n plus 1 factorial, x to the n plus 1. All absolute value limit times the reciprocal of the original. So x to the n goes on the bottom, and n factorial goes on top. And ratio test works nicely with these because the n factorials mostly cancel, the x's cancel except for one of them, and then the cubes do not cancel because you can't cancel inside the factor. But let's go ahead and simplify what we got. X is the only thing that could be negative, so we keep the absolute value on that. And then we've got n plus 1 cubed, and then n plus 1 n cubed. What you should be able to tell is if you look at the degrees of n, because it's a limit in n, x doesn't really matter. This is n to the 4th on bottom, n cubed on top. That's going to go to 0 no matter what, which is less than 1. That works all the time, so this would be an example where the radius is going to be infinite. So the interval of convergence that you see for that is going to be the whole line. A lot of times you'll get an x expression at the end, but not in this case. So I think you'll see that on the next one. So H is the other one I'm going to do, which has a different center. It's centered at 2. So we have n, and then 3 to the minus n, x minus 2 to the n. So let's put 3 to the n on the bottom. And then let's go ahead and do the ratio test. So this is going to be the limit as n goes to infinity. N plus 1, 3 to the n plus 1, x minus 2 to the n plus 1. Do the reciprocal. Do our cancellation. And then n and n plus 1 do not cancel. You keep the absolute value x minus 2, you keep the n plus 1, and you keep the 3n. Okay, now if you think about the degrees of n, it's the same, into the 1, into the 1. What are the leading coefficients? This is the leading coefficient at the top, and this is the one at the bottom. So this becomes our limit. And the ratio test says, hey, this will converge when that's less than 1. So I need to solve this. If you move the 3 over, now think about it this way. This is the distance between x and 2. So what numbers have distance from 2 less than 3? So on the number line, if you go to, here's 0, here's 1, here's 2, what numbers are within 3 units of 2? Well, minus 1 to 5. So you know the interval is minus 1 to 5, but you don't know if it's open or closed. You don't know if these should be brackets or parentheses, because the ratio test and the root test don't tell you when it equals 1. So we need to plug those numbers into the original expression. So when you plug in x equals 5, you get just n, because you get 3 to the n, 3 to the minus n, those cancel, and that's divergence. When you plug in minus 1, you get n, 3 to the minus n, minus 3 to the n. And so you get n minus 1 to the n. Go ahead and do the algebra to check me, but that's still something that doesn't go to 0. So it's also divergent. So this was actually correct, and it's open on both sides. You can get any case, though. You can get closed on both sides, closed on one side, closed on the other side, closed on either side. Those are all possible. Okay, so those are how you do those with the ratio test. The root test is a little different, but pretty much the same idea, and this should all be reviewed from Calc 2. All right, so let's look at number 4. So it says R is the radius of convergence for a power series. So, and infinitely many of the coefficients are non-zero integers. Okay, so infinitely many and are non-zero integers. And I want to prove that R is less than or equal to 1. Okay, so you don't have much to go on here, but we can actually use the root test here to get the idea. The ratio test is harder to think about, but roots of integers are a little easier to process. So if you think about all these non-zero integers, the absolute value of those ANs, these specific ones, is greater than or equal to 1, right, because they're integers, and now I'm doing absolute value. So alpha is, if we do the root test definition, you take the lim sup of these. Well, all of those are going to be greater than or equal to 1. And then we take the nth root, they're still greater than or equal to 1. So if you do the lim sup, that stays greater than or equal to 1. But remember that the radius should be 1 over alpha. Since alpha is greater than or equal to 1, this is less than or equal to 1. So that's just a quick application of the root test. All right, next we want to do number 7. And this one says you have a sequence that's bounded, but it diverges. Prove that the radius of convergence of the power series that pairs with it is equal to 1. So AN bounded, this is 7, this diverges. And we want to say that this power series has R exactly 1. Okay, well, let's make the AN, because it's bounded, it has some sort of bound, right? And that tells you that if you want to think about this kind of thing, right, this is less than or equal to m x n, thinking about the comparison test. And this would be, if you think about this series, this is convergent for f sub x less than 1, because it's basically a geometric series, right? So that implies that this would be convergent, which means the original, that's absolutely convergent, so this would converge for x less than or equal to 1. That was the comparison test. Anytime you see something's bounded in this chapter, you should think about the comparison test, because bounded gives you an inequality. That's what the comparison test wants. Okay, so that means R is less than or equal to 1, right? Or I should say R is greater than or equal to 1, because it works all the way up to the 1. So greater than or equal to 1. However, what happens at 1, if x equals 1, well, that diverges. So x equals 1 is not allowed, right? You can go up to your radius can go up to a certain point, but you can't skip it. So if it goes up to 1, nothing past that works. So that means R equals 1, and that input doesn't work. The interval of convergence looks like -1 to 1, and you know this side is open, and you don't know about this side, right? But you know it doesn't go past that, so the radius is 1. All right, going to number 8. They give this weird definition for a set, negative of a set, just flip all the numbers, and it says A is the interval of convergence for a power series. So you got this guy, and it's got interval of convergence A, and then show this guy, the alternating version, has interval negative A, which they define on the problem. It means like if you had like 3, 5, this would be -5 to -3. Flip all the numbers. That's just an example. Okay, so what happens here? Well, before, if x equals a, then, and it's good, then you would say that this converges, right? If I want to create that here, I'd have to put, if I put negative a in for, so that goes for this, and then you go for this one, you'd have minus 1 to the n, a n, minus a to the n, and then when you pull that negative out and cancel it, you get the same thing. The point I'm trying to make is that the first one converges at x equals a if and only if the second one has the alternation with it converges at x equals minus a. And so that is exactly what you're looking for. That concludes the problem. All right, we are done. Advanced Calc, that is the end of the ice sheets for the semester.